right. Um, did I start that? Yeah. So here are the current assignments. So remember that um, I did have to change the assignment on section 3.6. So make sure that you have that updated. That's going to be due on Thursday. So
Can you share your
tomorrow.
screen?
Oh, sorry. I forgot something. I just couldn't remember what it was. All right. So the assignment for section 3.6 is 52 and 54. Um, and then here's the assignment for section 4.3. Web assigned assignments 3.6 is due tomorrow and 4.1, 4.2 on Monday. The third exam, which covers the last chunk of material on the syllabus, so that's 3.1 to 3.6, 4.1 to 4.5. That's tentatively scheduled for Monday on the last week of class. And the final exam is on Thursday. So here's the calendar. So we have this week, the 12th through the 15th, next week, the 19th through the 22nd, and then the final week of classes here, 26th through the 29th. So we'll have the third exam on Monday, and then on the 27th and 28th, Tuesday, Wednesday, we'll review, and I'll have like a practice exam for you, practice final exam. The questions on the final exam will be uh, just questions very much like what are on exams 1, 2, and 3. Okay, so I'm not going to throw something at you. Okay. Okay. Um, very much like the questions from exams 1, 2, and 3. So I'm not going to put anything new. I mean, it's not the same questions, of course, but questions of exactly the same type. And then the final exam on the last day. There's no final exam period during the summer semester, so we have to do the final exam on the last day of class. Okay. So yesterday we finished lecturing on sections 4.1 and 4.2. So I just want to go over some problems on those, some of the discussion problems to start with. So 4.1, now which ones did I assign? 34 and 58. 34 and 58. Okay. And 4.2, which is very much the same, was 24 and 28. Yeah. So let's look at just some introductory type things in 4.1. How about number 20? So number 20 gives you two graphs, two functions, exponential functions. Fx equals 3/4 to the x, and Fx equals, or Gx equals 1.5 to the x. And graph both functions in the xy plane at the same at the same time. So 3/4 to the x, right? the base of the exponential function is always supposed to be positive, which 3/4 is. And 3/4 is less than 1. Right? So an exponential function always has this general shape where the x-axis acts as a horizontal asymptote in the positive direction. The positive x-axis is the horizontal asymptote when the base of the exponential function is less than 1. So this is 3/4 to the x because y equals, because 3/4 is less than 1. And the y-intercept is always just at 1. Unless you have a k in the front there, in which case it's at k. And then 1.5 to the x looks like that. It's the same type of graph, just spun around the y-axis. And this is because 1.5 is bigger than 1. Okay, so exponential functions, they always just look like that. Pretty simple graph. And the behavior of the function is that it grows very, very quickly. It's a very fast-growing function. Faster than any polynomial, eventually. All right, so armed with that example, let's look at, say, some graphing problems, number 31. So, graph fx equal to 10 to the x plus 3. So the graph of 10 to the x looks like that, right? So 10 to the x plus 3 is just obtained how? From this one. Right, I take the graph of 10 to the x and I do what to it to get to the graph of 10 to the x plus 3? What do I do?
Move it left 3.
Shift it left 3 units. 1, 2, 3, I guess, like that. So y equals 10 to the x plus 3. So if we make that one a different color, look nicer. Right, it's just that standard transformation of shifting to the left by 3 units. Right, so 3 units to the left. So with, so something similar to 34, graph y equals 10 to the x plus 3 minus 5, say. Well, if I'm going to do that graph, what's going to happen? Right, so first I took 10 to the x, shifted it left 3. Now if I want to get the graph of 10 to the x minus 5, I have to do what to the graph of 10 to the x plus 3? I have to take it and shift it how? Shift it down 5 units. Probably like right about there. Alright, shift it down 5. Okay, so just, similar sorts of ideas that we've discussed before, just exploring these ideas with exponential functions, how to take the standard graph and manipulate it so that you get, some variation of that graph. This is really the best way to understand graphs of simpler type functions. We all have these graphing calculators. Well, I don't, but you know, uh, you may have one, and probably you did because they forced it upon you in grade school. Um, so it's a plot by Texas Instruments uh, to use school age children to further their interests. They developed these calculators in the mid to late 80s. So, like when I was in high school, they just started coming out. And, we all thought they were very cool and such. But I remember Texas Instruments going bankrupt in the early 80s. And, then it really took off in the 90s all because of their calculator. Um, and, it doesn't really do much for you because the right way to understand these graphs of simpler functions is just like what we're doing here. Is just by taking one standard graph and doing these operations to them, shifting left and right, up and down, stretching up and down, stretching left and right. It gives you a better understanding of what these graphs are. When you just have the picture in front of you without any other context, well, it doesn't tell as much as you might like. All right, so exponential functions are used a lot in various modeling situations. So I assign number 58. So let's look at, say, number 59. So if $500 is invested at an interest rate of 3.75 per year, compounded quarterly, find the value of the investment after the given number of years. Okay, well, the compounded interest function, or formula, if you will, it looks like this. So if A is your initial invested amount, and R is the interest rate in decimal form rather than in percentage form. So 3.75, you have to divide by 100, 0.0375, like that. So that's the decimal form. 3.75%, that's the labeled form, or the percentage form. So this is an unlabeled quantity, that's a labeled quantity. And N is the number of compounding periods per year. And T is number of years. Then the value after T years is your initial amount, 1 plus r over n to the n t. All right, so that's your base function, your exponential function with this base here. The base changes with the interest rate and the number of compounding periods. Right, so they're asking about 1 year, 2 years, 10 years for this $500. So the value after 1 year, well, in this case, so in our problem, the value after 1 year is, V of t is equal to 500, 1 plus 0.0375 over 4 to the 4t. So let's get an actual number for that there. So where's my calculator? Is this one that I like? Yeah. So 0.0375 divided by 4 is that, plus 1. So 1.009375. To the 4t. So A, the value after 1 year is 500, 1.009375 to the 4th. Part B, the value after 2 years is 500, 1.009375 to the 8th. And after 10 years, 500, 1.009375 to the 40. All right, 1 year, 2 years, 10 years. So we got this number here. So 1.009375 to the 4th. So the exponent button on your calculator should look like that. Something like that. So to the 4th power, oops, that didn't work, did it? One 1.00935 to the 4th. So that times 100, or 500. $519 and how many cents? And 2 cents. All right, so after 1 year, that's how much that investment makes. Well, how much the investment is worth. I guess we should put equal. And after 2 years, so 1.009375 to the 8th power times 500, 538 and 75. And after 10 years, so to the 40 times 500, 726 and 23. All right, so that's the simple, interest, compounding interest formula and how that works. There's a lot of other neat formulas in finance, often dealing with these exponential expressions. There's the like installment loan formula for car loans and mortgage loans, and savings plan formulas for different types of saving plans and such. It's a pretty interesting topic, and we cover that sort of thing in one of our courses. I'm not sure which one it is. Um, I'm pretty sure we probably cover that stuff in our new actuarial science program. We must cover it in that. If you don't know what actuarial science is, it's a pretty interesting field, and it's got very very lucrative career paths in it. If you're interested in that, then you maybe you can ask. We can talk about that sometime. But anyway, there's that. So number 58 is very much like that. Other places, other types of problems with exponential expressions. Let's go on to section 4.2. So in section 4.2, we talk about exponential functions with the base e. So e was that special number called Euler's constant, which was 2.718 something something. So I assigned in this section numbers 24 and 28. So the radioactive decay thing. We covered an example like that before. Number 25, that's an interesting one. So a skydiver jumps from a reasonable height above the ground. The air resistance she experiences is proportional to her velocity. And the constant of proportionality is 0.2. It can be shown that the downward velocity of the skydiver at time t is as follows. So, they're not discussing the situation, the physics of the situation, really. But they're saying that the velocity of this skydiver at t seconds, I guess, so 1 minus e to the minus 0.2 t. So another one of these logistic type functions. So velocity in feet per second. So feet per second at t seconds. So that's the velocity of the skydiver as they go down, right? When somebody's skydiving, or when you throw something from a certain height, the velocity doesn't just keep increasing, right? It stops at some point because the air resistance gives it an upward force, whereas the gravity gives a downward force, and it reaches a sort of equilibrium at some point. And that can be described by this type of function, a logistic function. Find the initial velocity of the skydiver, point A. So initial velocity, right, that would be v, the velocity at time 0. So that's 180 times 1 minus e to the 0. E to the 0 is what? Right, we discussed this a while ago. Right, for any exponential function, if a is not equal to 0, then a to the 0 is equal to what? You'll remember?
1.
1. Not 0, 1. Right, because like a to the third over a to the third, right, is a to the 3 minus 3 is a to the 0. Right, but that's equal to 1, because anything divided by itself is 1. Right, if you said that it was 0, then this kind of identity that we use with exponential expressions wouldn't work. Right, so we covered that way back in chapter P, preliminaries or whatever. So that's equal to 1 here. So keep that in mind. So it's 180 times 0 is 0 feet per second, right? So as the person jumps or before they jump, their velocity is 0. B, find the velocity after 5 seconds, after 10 seconds, etc., etc. So velocity at 5 seconds, velocity at 10 seconds. So this is 180 times 1 minus e to the negative, so 0.2 times 5 is negative 1. And after 10 seconds, 1 minus e to the negative 2. Okay, so let's calculate those. Okay, so for this base e, you should have a button on your calculator that says e on it, or e to the x, perhaps. And depending on what kind of calculator you have, there's different ways of entering the expression in there. So in this type of calculator, so if you want to do like e to the third, it's just e right here. So it's 2.71828, so on and so on and so forth, to the third, something of that sort. So e to the third, 20.08. All right, or you might have one of those little solar calculators, uh, in which case it uses reverse notation. I don't know if any of you are using that, but if you are, that uses what's called reverse notation, and then you would hit like 3, and then you would hit the e to the x button, and the button would say e to the x on it. You'd say 3 and then hit e to the x, but this is not that. Graphing calculators are more like this one here. All right, so we're calculating this. So you have to start with the exponential expression typically. So e to the negative 1. So e to the xy, 1, and then negate it like that, is this quantity. And then I want it to be negative. It has to be negative, and then I'm going to add 1 to it. So negate it plus 1. Gives me this number times 180. 113.78 feet per second. And then for this one, so e to the exponent 2 negative. So the negative button is in reverse notation with this one. You can't say negative, hit the negative button, then put 2. You have to hit the 2 and then push the negative button. Anyway, we get this. That's got to be negative because we need to add it to 1. We'll subtract it from 1. So 0.86 times 180, 155.64. Oops, what was it? 155 feet per second. Draw a graph of the velocity function. So with these logistic functions, they look like this. (180) 1 minus e to the minus 0.2t. So as long as you got a 1 here, as long as you have a 1 here, you're going to have a horizontal asymptote at 180. And then the question, is it a logistic growth or a logistic decay? Right, so here's y equal to 180 right there. And then it starts at 0. Right? This is the t-axis, and this is the y-axis. And then, at t equal to 0, as we found up here, the initial velocity is 0. And then it grows 113, 155, so on and so forth. So at 5 seconds, 113, at 10 seconds, 155. So, I don't know. So this is 90 right here. So 113, 155. So it's this exponential curve. I had to mess it up at the end there. Right, so the velocity keeps growing up to 180 feet per second, getting closer and closer, but never actually quite getting there. That's just a model of what the velocity is. Of course, in a real situation, the velocity will actually reach, some constant speed. Here it says it's increasing and increasing, but at some point there's there's essentially no difference between 180 and what your velocity is, or the difference is effectively 0 because it's just so tiny. All right. So logistic type function, and this type of exponential function, it doesn't extend down here because of course you're not talking about negative quantities of time. But if you did extend it, it would look like that. It's the usual exponential curve, just you're only using this part of it. So this is logistic growth. Logistic decay, you have a horizontal asymptote here, and then some initial quantity there, and it looks like that. This is logistic growth. And this is logistic decay. All right. And then 26. Was it 26 I assigned? '28. Oh, 26 we went over yesterday. 28. Okay. So 28 is one of these population models. Well, that's very much similar to what we just did. So I'll let you take a look at that one. 27. Yeah, 27 is similar to that. But let's move on to section 4.3 at this point. So, along with exponential functions, their companions are these logarithmic functions. So the definition is as follows. So if b to the y is equal to a, like this, if you have this exponential expression, base b to the exponent y is equal to a, well, let's call it e. Base b to the exponent e is equal to a, then we say that the log base b of a is equal to e. So in the exponential expression, the base goes down here. The argument of the function is this right here. the result of the exponential expression, and the value of the log is the exponent. What this means is that so note the following. Well, let's take an example of this. So, for example, the log base 10 of 100 is 2, right? Because 100 is equal to 10 squared. The log base 10 of 1,000,000 is equal to 6, because 10, or 1,000,000, is 10 to the 6th power. The log base 10 of, say, 0.001 is equal to -3, because 0.001 is 10 to the -3. So that would be, some examples with base 10 logarithm. And then there's, other logarithms, different bases that are commonly used. Log base 2 of 16, well, that's 4, right? Because 2 to the 4th is 16. Log base 2 of, say, the square root of 32. Log base 2 of the square root of 32. Okay, well, that's equal to, anyone know? Anyone see what that's supposed to be? Well, 2 to the 5th is 32. And then the square root thing corresponds to what as an exponent? Right, a 1/2, right? So this is 5/2, because the square root of 32 is the square root of 2 to the 5th, which is 2 to the 5th, and then the square root is a 1/2 power. Right, so it's 2 to the 5/2. 25, 2 to the 5th. And then the log base 2 of, say, 1 over 16. Well, that's -4, because 2 to the -4 is 1 over 2 to the 4 is 1 over 16. So on and so forth. So the way the logarithm is defined now yields the following. Right, so if b to the e is equal to a, then the log base b of a is e. So let's dispense with the letter a entirely, and let's just put b to the e inside there. Right, so here is the definition. Okay, forget about a and just use b to the e. So the log base b of b to the e, right? If a is b to the e, then the log base b of a is e. Well, the log base b of a is just the log base b of b to the e, because a is b to the e is equal to e. Right? So when I do the composition of the log function with base b and argument b to the e, it's just e. They sort of cancel each other out, the exponential function and the logarithm. Similarly, and we get this. In a similar fashion, b to the log base b of x, say, is just equal to x. Or I guess I should put, no, we'll just put an x there. b, so the log of a value is the exponent you need to take the exponential function with base b to that value. Right? So it's the exponent of the number as an exponential with base b. So when I take b to the exact exponent for b to get x, then I get x. So what am I trying to say here? So in other words, if f of x is a to the x, and g of x, let's say b to the x, is the log base b of x, then the composition f following g of x is f of g of x. Well, f of x is, g of x is log base b of x. So that's f of the log base b of x. And then f is the exponential function, so it's b to the log base b of x, which is just x. And g following f of x is equal to g of f of x. F of x is the exponential function b to the x, and g is the log, which again is just x. So what are we saying about the exponential function with base b and the log function with base b? What's their relationship if their compositions are always just x? What are we saying about those two functions, f and g, the exponent and the log, if their compositions are always just x? They are what? What's the relationship?
Are they equal?
Not equal, but what's the, starts with I?
Inverse?
Inverse functions, right. They're inverse functions of each other. F of x, well, g of x, equal to the log base b of x is the inverse function for f of x equal to b to the x. So every exponential function has this inverse function called the log base b. Right? So different bases have different, different inverses. In some ways, they're all kind of the same. whatever base you use. In some ways, they're always the same, in which case you kind of always boil it down to using base e or base 10 or base 2. We'll talk about that later. So anyway, since they're inverse functions, the graph of the log looks like this. Y equals b to the x and y equals log base b to the x look like this. So the exponential function, we've been talking about how it looks like that. Here is the line y equals x. Remember, so this is y equals b to the x. The inverse function of a function, actually let me make this actually better looking. The graph of an inverse function is obtained by reflecting around the line y equals x. The graph of the inverse function is obtained by reflecting the graph of the function around the line y equals x. So it looks like this. Log base b of x. Here the y-intercept is 1, so here the x-intercept is at 1. This one has the negative x-axis as a horizontal asymptote, so the log function has the negative y-axis as a vertical asymptote. So notice that the domain of the log base b of x is 0 to plus infinity. That is all x bigger than 0. You can't take the log of 0. Exponential functions always positive, never 0. Therefore, the log function, whose inverse is the inverse of the exponential function, the domain has to be just all positive numbers, because that's the range of b of x. The range of b of x, b to the x, is 0 to plus infinity. Another interesting thing to notice, exponential functions are again considered to be very fast-growing functions. So since this one is a very fast growth function, when you reflect it around that line, you have this log, which is the primary example of a slow-growing function. It grows more slowly than like square root of x, more slowly than the third root of x. So exponential functions, they are faster growing than any polynomial, and log functions are slower growing than any sort of root function. Square root, third root, fifth root, whatnot. All right. So speaking of the domain, what is the domain of the function f of x equal to the log base 2 of 9 minus x squared? Well, in order for a log to be defined, the argument must be positive. Okay, so this expression will be defined as long as 9 minus x squared is greater than 0. Not bigger than or equal to, right? Like for a square root, right, all you need here is that 9 minus x squared is bigger than or equal to 0. Because you can take the square root of 0. Square root of 0 is 0. The square root of the log of 0, you can't, that's not defined. Because it's the inverse of an exponential function. An exponential function is never equal to 0. Okay, so strictly greater than 0. So this is 3 minus x times 3 plus x, bigger than 0. Putting these on a number line. Here's the minus 3, here's the positive 3. And if you test these intervals, then you just get that the polynomial is negative here, positive here, negative here. Right, so the domain is minus 3 to 3. All right. So some special bases or commonly used bases for logarithms are as follows. So this is just some notation. So the log base 10 of x is usually written, so that's called the common logarithm. The log base 10 of x is usually written as just log of x. So if you have just log of x without a base, they mean log base 10. The natural logarithm the log base e, so e is the Euler's constant, is usually written as ln, natural log of x. Log natural of x. So ln. And the binary logarithm, the log base 2 of x is usually written lg x. Okay, so those are the most commonly used bases. The third one, the binary logarithm, is the least common. The most common is the natural logarithm, I believe. That's the one you'll see used most often. Log base 2, you only see that really in computer science type applications. And this one, like in finance type applications, I believe they use log base 10 fairly often. But so these are the commonly used bases. And if you look on your calculator, so see, it usually will have a button. It won't have a button for every logarithm. It'll just have a button for the common logarithm, log base 10, which is just log, and the natural log, ln. So, like on a calculator, the natural log of 1. Right? So whatever sort of base you're using, yeah, so this uses reverse notation here. So first I hit the 1 and then ln, and it gives me 0. So it says what I entered right here. So that's ln of 1. So this is reverse notation. So if you want to do like, let's see, 100. So here's 1,000. So the log of 1,000 is 3. Log base 10 of 1,000 is 3. So first you hit the number, and then you hit the log button. That's reverse notation. On a graphing calculator, first you hit the log button, and then it'll give you a set of parentheses, and then you put the argument in there. So that's the more common notation. The just left to right notation. But sometimes calculators use reverse notation like this one. And if you got those little solar power jobbies, those also use reverse notation. So anyway, the natural log of 1 is 0. The natural log of, say, 5. So 5 natural log right there. 1.60937. The natural log of 2, believe it or not, is actually a number that pops up in some interesting calculations that you'll see in Calculus 2 if you take that. But that's 0.693147. Approximately that. The natural log of 2 is actually, well, I'm not gonna get into that. Okay, so, well, that's the end of this section. I think we could just leave it at that for today. I don't think we should go on to the next section. So tomorrow we'll go over some problems in section 5.2, or this was, no, 4.3. So this section was just introducing that logarithm function. The next section is going to talk about properties that the logarithm functions have. The logarithm function sometimes tends to be a little confusing for students the first time you see it, or anytime you see it, I guess. So if you spend a little extra time with it, you'll have a better chance of success in dealing with it. Okay, so tomorrow we'll go on to section 4.4, which is properties of logarithms, after discussing a few problems here. Okay, all right, everyone, have a good day, and I will see you tomorrow.